October 7, 2025 should have marked a turning point in interstellar astronomy. After months of building anticipation, the European Space Agency released the first official images of Three-Eyed Atlas, an interstellar comet making its historic pass by Mars. The astronomical community had been electrified with excitement for weeks. This was a visitor from beyond our solar system, a precious opportunity to study material that originated in another stellar neighborhood entirely. Scientists and enthusiasts alike expected breathtaking imagery and sharp details that would fill textbooks and capture imaginations worldwide. What the world received instead was deeply anticlimactic: a single blurry dot, barely distinguishable from the digital noise scattered around it. At 9:22 UTC, the images appeared across ESA's official channels. Within minutes, the world's largest science accounts, space enthusiasts, and even meme pages were circulating the same disappointing frame. By midday, ESA was trending in 4 languages across social media platforms. Hashtags like PyFuzzyDot and PyWhereErathapix surged across X and Reddit, with amateur analysts dissecting every pixel, desperately searching for hidden details that simply weren't there. The public reaction transcended mere disappointment and evolved into genuine outrage. Side-by-side comparisons flooded social media feeds, showing backyard telescope captures that appeared to contain more apparent detail than images from a billion-euro Mars orbiter. Comment sections erupted with accusations and conspiracy theories. Was ESA deliberately concealing information? Why were NASA, China, and the UAE maintaining simultaneous radio silence? With every unanswered question, public pressure for genuine explanations intensified, and wild speculation began multiplying in the vacuum created by official silence. Understanding what happened requires examining the instrument itself. The CASS camera aboard the ExoMars Trace Gas Orbiter was never engineered to chase interstellar visitors through deep space. Its primary mission involves mapping the Martian surface in sharp color, tracking landslides, and searching for subtle changes in dust patterns and frost distribution across the planet's varied terrain. The camera excels at its intended purpose, but pointing it at a target 30 million kilometers away pushed it far beyond its design parameters. At that distance, each pixel on CASS covers approximately 340 kilometers, an area large enough to completely engulf entire Martian volcanoes, much less a comet nucleus that might measure only a few dozen kilometers wide. The camera's resolution of 1136 microradians per pixel establishes an absolute physical limit. Regardless of how perfectly the focus is calibrated or how long the exposure lasts, anything smaller than a single pixel inevitably becomes a blur, its light smeared across the sensor surface. Nick Thomas, the principal investigator for the CASS instrument, candidly called it a stretch, even to achieve a detection. The comet was at least 10,000 times fainter than the surface features CASS was built to image. The engineering team stacked multiple exposures, carefully tuned the tracking systems, and squeezed every possible bit of signal from the noise. The result, that infamous fuzzy dot, wasn't evidence of a cover-up but rather a demonstration of an insurmountable technical ceiling. The coma, a massive cloud of gas and dust extending thousands of kilometers in every direction, blended seamlessly into the background radiation. Meanwhile, the nucleus itself was lost entirely within the limitations of pixel resolution. The physics proved unyielding. At these distances, even the most sophisticated hardware orbiting Mars could only confirm the comet's presence, not reveal its secrets or structure. The public desperately wanted a portrait. The camera could deliver only a fingerprint. The next hope for meaningful detail would have to come from an entirely different instrument or a fundamentally different orbital perspective. That hope focused on HiRISE, the high-resolution camera aboard NASA's Mars Reconnaissance Orbiter. This instrument represents some of the finest imaging technology ever sent to another planet. Its exceptional optics can map individual rover tracks from orbit, distinguishing tire treads in Martian dust. At 30 million kilometers, scientists calculated it promised at least a glimpse, perhaps a few precious pixels worth of data showing Three-Eyed Atlas's core structure. But as the flyby unfolded, HiRISE went completely dark. The U.S. government shutdown, which began on October 1st, froze the entire operational chain. No command uplinks could be sent, no status logs were updated, no public data releases occurred. The official channels fell silent for days on end. Amateur astronomers and professional researchers alike repeatedly refreshed the HiRISE data archive, waiting desperately for any sign of the observation campaign. Nothing appeared. Even the planning files, normally posted well in advance of any observation sequence, were conspicuously absent. With NASA's feeds frozen solid, speculation naturally turned toward Mars's other observational assets. China's Tianwen-1 orbiter and the UAE's HOPE mission had both actively tracked the comet's approach in the days leading up to the flyby. Yet neither space agency released images, official statements, or even a simple denial of having captured data. The silence deepened and took on an ominous quality. Some observers pointed to the government shutdown as the obvious culprit behind the NASA silence, but this explanation couldn't account for why three separate space agencies operating on two different continents would all maintain radio silence simultaneously. In the complete absence of official data, rumors rushed in to fill the expanding void. Every hour without answers drew intensified attention to what was missing, not merely sharper images, but the unsettling sense that the world's most capable cameras were somehow being deliberately muzzled. HiRISE's conspicuous absence became the central story. This missing crown jewel left the internet community hungry for any outside evidence whatsoever, and every unanswered question fed growing suspicions that something significant was being deliberately kept from public view. In the hours immediately following ESA's blurry dot going viral, what became known as the Homage Wars erupted across social media and astronomy forums. Amateur astronomers from Italy to Japan posted their own processed versions of telescope observations. Some featured deep stacks combining dozens of individual frames, while others employed AI upscaling filters that promised to reveal hidden structural details. By October 9th, the internet had fractured into two opposing camps engaged in increasingly heated debate. One faction claimed to see a sharp core structure, perhaps even hints of a tail or jet features, arguing passionately that backyard telescopes operated by dedicated amateurs had somehow outperformed a billion-euro space agency orbiter. The opposing camp warned that every new claimed detail was merely an illusion, ghosts born from aggressive overprocessing techniques and wishful interpretation of noise patterns. Maya Trin, a well-respected comet hunter from Melbourne, became the unofficial spokesperson for the first camp. She published a sequence of progressively processed images, each more enhanced than the last, with detailed annotations pointing to what she characterized as non-random streaks around the nucleus region. Her posts accumulated tens of thousands of shares within hours, fueling waves of speculation about what professional astronomers were either missing or deliberately hiding from public scrutiny. Professional astronomers mounted a vigorous counteroffensive, posting detailed side-by-side comparisons and running sophisticated simulations to demonstrate their points. They showed conclusively how stacking faint frames can amplify background noise patterns, transforming random cosmic rays and hot pixels into false structural features that appear meaningful to untrained eyes. AI upscaling algorithms, they argued with increasing frustration, only made these artifacts appear sharper and more convincing without improving the underlying science or adding genuine information. The debate rapidly became intensely technical. Specialized terms like sigma clipping deconvolution algorithms and pareidolia began trending across astronomy forums as users attempted to reverse engineer ground truth from ambiguous raw data. Some knowledgeable commenters pointed out that even a perfect stack processed at Cassis's native 340 km per pixel scale could never resolve a comet nucleus measuring only a fraction of that size. The sharpest amateur images, when their processing pipelines were traced back carefully, often relied on aggressive enhancement techniques that introduced more legitimate questions than they answered. With every newly processed frame circulating through social media, the boundary between genuine discovery and comforting illusion grew increasingly blurred. The internet's insatiable hunger for dramatic details outpaced what the available data could honestly provide, and calls for rigorous, transparent analysis methodologies grew louder from the scientific community. If there was genuinely something unusual to see, it would require far more than clever software tricks to prove it conclusively. Anonymous posts claiming insider knowledge began circulating even before the first ESA frames finished trending across platforms. As this rumor ecosystem expanded and evolved, demands for real, verifiable data intensified. The internet's appetite for concrete answers now hinged entirely on the next round of measurable facts, precise trajectory mathematics, radio signal detections, anything that could be independently tested and verified. Until such evidence emerged, the burden of proof remained squarely with those making extraordinary claims, not with the skeptics questioning them. Mallory Lefferland, shift lead for NASA's Perseverance rover, faced an unusual problem that didn't appear in any mission checklist. The rover's navigation camera was never designed to chase comets, much less one racing past Mars at nearly 90 kilometers per second. Nevertheless, on October 7th, she authorized a special observation sequence, 10 minutes of continuous sky exposures, hoping to catch even a trace of three-eyed Atlas as it tore through Jezero Crater's field of view. The raw frames revealed a single faint streak measuring just over a pixel in width, stretching diagonally across the image frame. On first inspection, it resembled a digital glitch or cosmic ray hit, but the timing matched the comet's predicted passage to within mere seconds. The mathematics behind this smear was straightforward, but the implications proved far more complex. At 90 kilometers per second, Three-Eyed Atlas would cover approximately 54,000 kilometers in 10 minutes, precisely matching the measured length of the navigation camera streak. If the exposure lasted the full 10-minute sequence, the streak fit the theoretical model perfectly for motion blur, a distant object moving at tremendous velocity, too faint for any single frame but visible as an integrated smear when light is collected over extended time. However, a troubling alternative existed. If the camera had actually taken a single short exposure rather than a long integration, the source would need to be much closer, perhaps even in Mars orbit, to produce an identical length streak. Without access to the original flight's file headers containing precise exposure metadata, the exact timing and cadence remained locked within the rover's telemetry logs. Every calculation and interpretation depended critically on this missing technical detail. Lefferland's decision transformed a vague internet rumor into a testable scientific claim. The navigation camera streak became the first concrete numerical data point in an ocean of speculation, a 54,000-kilometer question mark hanging over the entire event. For subsequent rounds of radio listening campaigns and trajectory verification checks, this measurement would establish the evidentiary standard separating legitimate data from meaningless noise. A trajectory line projected backward from Jezero Crater on October 7th pointed almost directly toward a patch of sky famous in Ceti circles for one thing, the location of the 00 signal. In August 1977, a radio telescope at Ohio State University detected a remarkable 72-second burst at 420 megahertz, a hydrogen line frequency. Despite decades of searching, its source was never identified, but those coordinates lingered in astronomical databases and popular imagination. Now, with Three-Eyed Atlas passing within a handful of degrees of that same region, the geometric coincidence proved impossible for many to ignore. Forums filled rapidly with back-of-the-envelope calculations. To match the W signal's observed strength from a hypothetical transmitter located 600 astronomical units away, you would require at least half a gigawatt of power, possibly 2 gigawatts, if directing a focused antenna beam straight toward Earth. That represents the continuous output of a major power plant being beamed through the void of space. Yet despite all the excited chatter and speculation, no public observatory released hydrogen line spectroscopic data from the flyby period. No coordinated listening campaign results appeared. No raw spectrum dumps were shared. Not even null results were published. The silence wasn't merely optical anymore, it extended to radio frequencies as well. On October 29th, Three-Eyed Atlas slipped behind the sun from Earth's perspective, vanishing into solar glare so intense that even the most powerful telescopes were rendered completely blind. For nearly 40 hours, no ground-based observatory could track it. The comet's solar elongation angle shrank below safe operational limits for all but the most heavily shielded instruments designed specifically for solar observation. During this observational blackout, every theory found room to grow and evolve unchecked. Some astronomers issued warnings about natural outbursts or possible fragmentation events, the typical fate awaiting comets under intense solar heating and tidal stress. Others, carefully examining orbital projection models, wondered aloud whether a maneuver, something engineered rather than natural, might be unfolding completely out of sight during this critical window. The Galileo Project, a scientific team dedicated to searching for signs of non-natural technology in space, announced around the clock monitoring watch on all available radio and optical channels, hoping to detect any anomalous signals as the object rounded perihelion at its closest approach to the Sun. Early November brings a rigorous checklist of observational tests for Three Eyes Atlas. Astronomers are scrutinizing brightness curves, searching for sudden drops or unexpected surges that could signal fragmentation events or unusual activity. Orbital models continuously run on incoming data, checking for tiny deflections that might indicate outgassing jets or something stranger still. Each measurement functions as a pass or fail test of competing hypotheses. Does the comet's light curve fade as natural models predict, or does it fragment into multiple pieces? Trajectory predictions are being checked against observational reality, looking for any unexplained perturbations or course changes. Meanwhile, the JUICE spacecraft awaits its scheduled observation window later in November. Its sophisticated instruments promise an entirely fresh perspective on the comet, but the raw data won't reach Earth for processing until well into 2026 due to communication bandwidth limitations and spacecraft geometry. Until that time arrives, every subtle shift in the comet's trajectory or brightness becomes a potential clue, and every delay in official data releases keeps the world guessing about what survived its harrowing passage around the Sun. October's skies didn't belong exclusively to Three-Eyed Atlas. Just days before the comet's Mars flyby, a near-Earth object cataloged as 2025 TF skimmed past Earth, slipping inside the orbital radius of GPS satellites without any advance warning whatsoever. The asteroid, measuring only a few meters across, evaded detection by every major survey system until it was nearly overhead. This served as a stark reminder that even in an era of comprehensive all-sky monitoring networks, objects that are both small and fast moving can still remain effectively invisible until the last possible moment. Two other comets simultaneously set their own unpredictable courses through the inner solar system. Comet Seda 2023A3 Sachinchen began brightening weeks ahead of published schedule predictions, strongly suggesting a possible outburst event. Comet CB 2025 R2 Swan drew particular attention for its remarkably close approach, passing just 0.26 astronomical units from Earth and raising both hopes for spectacular tail development and concerns about sudden fragmentation. Each event collectively underscored the persistent limitations of current space surveillance capabilities, where the next surprise visitor could emerge from any direction at virtually any scale with minimal warning. On October 7 and 25, the European Space Agency released the first official images of Three-Eyed Atlas, just a single blurred pixel, sparking immediate global debate and urgent calls for transparency from space agencies worldwide. The frustratingly low detail resulted from CASIS's fundamental technical limitations, not from deliberate suppression or conspiracy. Yet the simultaneous silence maintained by Harris, Tianwen-1, and Hope left critical data gaps completely unexplained, fueling continued speculation. Despite viral amateur images and persistent rumors suggesting unusual chemical emissions or precision trajectory maneuvers, no official evidence has emerged confirming any of these extraordinary claims. The Perseverance navigation camera streak matched expected motion blur characteristics for an object traveling at 90 kilometers per second, though alternative explanations involving closer objects could not be completely ruled out based on available metadata. As Three-Eyed Atlas vanished behind the Sun at perihelion, observers worldwide turned their attention to early November observations for any signs of fragmentation events or unexplained trajectory shifts. The delayed JUICE spacecraft observations and the recent undetected close passage of near-Earth object 2025 TF underscore the continuing fundamental challenges in monitoring fast, unpredictable visitors to our solar neighborhood. To date, the true nature and composition of Three-Eyed Atlas remains genuinely unsolved, highlighting both the technological limits and the critical importance of open data sharing practices in planetary science.